Hello, I'm Mike McCulloch. So today I'd like to talk about Newton's gravitational constant, and I've come here to Buckfast in Devon, and you can see the Abbey behind me to talk about this. So as you know, Newton's gravitational constant appears in Newton's gravitational law, and it's always been derived before by experiment. They've done it empirically by measuring the force between known masses in laboratories, and they worked out its value that way. But it turns out you can actually derive it from quantized inertia, this constant, within the uncertainties. And I'll try and explain how. So in quantized inertia, the basic idea is that nothing must exist that can't be seen directly. So in any volume of space, any accelerating object will see Unruh waves, whose length is determined by the acceleration of that body. So the slower the acceleration, the longer the Unruh waves are. Now this means that you can't have an acceleration below a certain value, because the Unruh waves will be longer than the observable universe, which would be ridiculous. You won't be able to measure them, and so by this philosophical principle they should not exist. And this is how quantized inertia is derived, which tends to work very well predicting galaxies, that sort of thing. So, but what this means is that in any given volume or size of universe, there must be an acceleration such that it keeps the Unruh waves shorter than the size of that universe. So you can write down an equation which I show here. So gm over r squared has got to be, that's the gravitational acceleration, has got to be greater than this minimum, which turns out to be 2c squared over theta, where capital theta is the Hubble diameter, the diameter of the observable universe. So this comes from quantized inertia, and by a little bit of manipulation you can do several things with it. For example, if you get rid of an r on each side and theta is 2 times the radius, then you can say that the potential energy equals the kinetic energy. And this explains an observation that has been made, that the potential energy of the cosmos and its kinetic energy are usually about equal. And so that follows from quantized inertia. So it's never been understood before how it is that the universe is just on the threshold of being bound and not, because its potential energy is equal roughly to its kinetic energy. But this explains it, and it explains it for all time as well. It's the same at all times, no matter what the size of the universe is. The other thing you can do is rearrange this formula to give g. So g turns out to be c squared m over theta. Sorry, c squared theta over m. And now this relation has been guessed at in the past, many decades ago, by Dirac and by Sciama, but they never had a reason for deriving it. But quantized inertia provides a reason. It gives a direct derivation of this equation. I think it should be c squared theta over 2m, actually. So here we have g, Newton's gravitational constant, derived from properties which are all known. So everything on the right hand side is, well, more or less known. We know the speed of light, which is c. We know the mass of the cosmos, well, roughly, because we can count the stars and we can estimate it. And we know the Hubble diameter. Again, roughly, it's supposed to be, the error in that is supposed to be 5%, 10%. So if you put in the known values of these, you get something which is consistent with g. And although there's a huge range on the possible values, this is a very interesting agreement, because the exponents on some of these properties are incredibly large. For example, the mass of the universe is something like 10 to the 53 kilograms. So the fact that it agrees is likely meaningful. So yeah, so this means that in physics we can now well, in principle at least, get rid of big G in all these equations and replace them with this other relation, which is composed of observed quantities. So this means that quantized inertia gets rid of an arbitrary parameter from physics. So, okay, so I hope you've enjoyed this this short and enjoyed looking at Buckfast Abbey, and I look forward to speaking to you next time. Goodbye.